Hi there, this video is for section 2.4. We're going to verify the value of a limit. This is oftentimes called verifying a limit using epsilon and delta, but don't worry about the epsilon delta. They're just letters like A and B, or more specifically, a Greek E and a Greek D, but we're just going to verify the value of a limit. So why do we need to do this? Well, we have done things with limits before, trying to get closer and closer and closer. For example, the limit as x approaches zero, and we use numbers of x very, very close to zero to see what the y value becomes. So here's an example of a function. I have this sine function that I've graphed right here. And you may notice that when I plug in the number zero, it is not defined, it's undefined. So we'd like to know what happens at this point where x equals zero. Well, graphically, it certainly looks like 4. We can put in some numbers like 0.1, and that's 3.97. That's pretty close to 4. And we can do a sequence of values that are getting closer to 0. And you might see that the number is getting closer to 4. Eventually, the Desmos has to round. We can use a more sophisticated graphing calculator. It'll give us more decimal places, but it certainly looks like it's getting closer and closer. Here, let's fix that one. There we go. To 4. We can even go from the negative side to like negative 0.01. And you can see also it's getting closer and closer to 4. How do we know for sure it actually is 4? Like maybe it gets to 3.9999975 and that's it, right? We want to have an ability to know when does it actually have a limit of precisely 4 and when does it not. And that's the point of this particular section in 2.4 is we're going to be investigating how we can determine that. All right, so let me go to our page over here and I'll zoom in a little bit and I'll tell you how this works. So when we're doing a limit and we think we have an answer, 4 in the previous example, or in this particular case, we're going to be looking at a limit and we think the answer is going to be something, like 3 or something like that. How do we know that it's exactly 3? How do we know 3 is the right answer and it's not like, 2.975 or something? Well, if it weren't 3, if the answer weren't 3, there would be some difference, something where we couldn't get closer than 2.975 or something. There'd be some point in which we could say, okay, it can get no closer than, 0.0025 or something, right? So we could have some separation between what we find by taking a table and what we actually theoretically think the answer is going to be. So that's how our argument's going to go. Before we do this, I'm going to just clarify some notation for folks who haven't done absolute values and less than signs recently. These are used quite frequently in higher level mathematics, and it looks pretty complicated. So this one right here says the absolute value of x minus 4 is less than 3. If I subtract two things, that just means the distance. So that means the distance between x and 4 is always smaller than 3. I find it much easier to visualize this. This is the x-axis. This is the number 4. And the distance between any x value and 4 has to be less than 3. So if I went 3 this way, I would end up to 7. And if I went 3 this way, I would end up to 1. So all the x values between 1 and 7, all of these x values, right? 4 and up or down 3 is what this inequality represents. So although it may look like a bunch of math symbols, what they're just saying is that x is between 4 plus 3 and 4 minus 3. And likewise, for the second example, if you want to think about that for a second, we have the y-axis. I can make the y-axis horizontal if I want. I'm going to do it. And we're saying the distance between y and 7 is at most 2. So that means 7 is right here. And it can go up to 9. And it can go down to 5. So the distance between any number y and 7 is always smaller than 2. And lastly, this one over here, x minus minus 5. You'll see this usually written as x plus 5. So just be aware that when they write the plus, it's really minus a minus. I wrote it that way because remember, the minus says the distance between. So this says the distance between any number x and negative 5 is at most 1. So negative 5 is our center point. And then we go 1 up and we go 1 down. And that's what that's representing. So just kind of clarify, the absolute value inequalities are just a range of numbers, right? Starting with that inside one and just going as far as the radius given by the outside one. Okay, so let's go ahead and show you the argument. I'm going to do a couple of these. The first one I'm going to do is a very simple function where we kind of already know the answer just because it's so simple of a function. However, I'm going to use that just to make the algebra simple, and then we'll do a more complicated one after this. So what is this problem asking us to verify? Well, it wants us to verify this limit as x approaches 1 of x cubed plus 2. Right? So if you just think about this, when x cubed plus 2, and you have x getting closer and closer and closer to 1, then this gets closer and closer to 1 cubed plus 2. And 1.00001 cubed is still basically 1, and 1 plus 2 is 3. So we think the answer is 3. And we can go over to Desmos, and I have this already typed in, so let me get rid of these guys here. So there's my function, and we are looking to see what happens around x equals 1. So I can put 1 here in for my table, and you can see it says 3. I can even make that show up here. There's 1 comma 3. As I said, this is a very simple function. This is going to be quite obvious that the answer is 3, but we're going to go through the steps so you can see how we verify this, even though now we know, of course, the answer is already 1. All right, once again, we can plug in numbers that are close to 1, like 1.01 or 1.0001, or we can come from the other side. To the left of 1 would be something like 0.9 or 0.999, and you can get the idea from the data. In fact, it's equal to 3. Okay, so here's the argument. If it weren't equal to 3, if someone says, I really don't believe this math mumbo jumbo, if it's not equal to 3, they need to say, how close does it get? Does it get like very close or just kind of close? Like, what's the closest it gets to 3? Because if it ain't 3, it's somewhere else. It's some distance away from 3. So we're going to do an example here. Suppose our, doubter says that it never gets closer than 0.1 to 3. So maybe it gets to 0.29, but it doesn't get any bigger than 0.9. So we're going to refute that claim. We're going to refute the claim that it never gets closer than 0.1 to 3. All we need to do is find an x value where it's closer than 0.1 from 3. Now, 0.1 from 3, right, if you think about that, would be something like 2.9 or 3.1, right? So we need something that's closer than either 2.9 or 3.1. And I think we already did that. Yeah, so here's 1.01 is 3.03, and that's definitely closer than 0.1, right? 3.1, this is closer than 3.1, right? But our doubter is really animate, and they're going to say, okay, well, I know you got it closer than 0.1, but what about 0.00001? I don't think it ever gets closer than 0.00001. So you're like, okay, so we can try to guess and check until we can find numbers that are closer than that threshold. But we're going to use just some math algebra just to nip this in the bud. No matter what number they give us, we can always find something closer than that. All right, so let me first show you the algebra with the 0.1, right? So we have this claim that we're going to refute. This claim right here says that the difference between y and our answer 3 cannot be smaller than 1. So we have this y minus 3 is less than 0.1. We need to say we can find an x value that gets closer than 0.1. Okay, so we know what y is. Y is given by this function. It's x cubed plus 2. So let's put x cubed plus 2 in there. Minus 3 is less than 0.1. And we'll just combine this together real quick. All right, so you can maybe see why I did this little review of absolute value inequalities. So this is basically saying that the difference between x cubed and 1 is less than 0.1, right? So we know that we have a series of values, and we have an x cubed here, and we know the difference between it and 1 is 0.1. I'm going to write this as an inequality instead. So x cubed minus 1, that difference has to be between 0.1 and negative 0.1. So that's the, range of values that we have for this thing. Let's just add 1 to both sides. And there's 2 both sides, so we'll add 1 to all both sides. And that gives x cubed is in between 1.1, and over here we have 0.9. And lastly, we're going to cube root to get rid of the x cubed thing. Or I guess we could do it to the 1/3 exponent. That's, I guess, more calculusy when we do fractional exponents. So as long as x is between 0.9 to the 1/3 or 1.1 to the 1/3, as long as we have an x in that little range, we know that the difference is going to be smaller than 0.1. So let's find out what, for example, 1.1, let's try this one on the right since we were doing bigger numbers. 1.1 to the 1/3. So I'll do something like 1.1, and I'll use some parentheses perhaps. And I'm going to raise it to the 1/3 power. And that gives us a value of x, 1.03. So as long as we had a number in our table that's smaller than 1.03, we would have gotten something that's closer than 0.1. So for example, I'll go over here and I'll put in 1.03228, as long as it's smaller than this number, right? So I'll just leave off some of these extra digits. You can see that this is closer than 0.1. 3.09 is closer than 3.10, right? So we're going to be able to do this. Now, the reason why I did this algebraically is because we don't have to do this with 0.1. We could do this with any number, right? We can even set up a formula where we can do this exact same situation, but we can do it with a letter instead of a number like 0.1, so that no matter what they come back with, we can say, oh yeah, I can find an answer. And the letter that they usually use instead of a C or something, they use is this E number, the epsilon that I referred to before. But the process is exactly the same. We're still going to put in the y value or the y function in for y. And then we're still going to simplify. All the steps are going to be the same, except that we're using the letter epsilon, this Greek E, instead of 0.1. So I'll get, well, this is negative E or negative epsilon to epsilon. And we have x cubed minus 1 in there. And then I'll add 1 to both sides, or all 3 sides, I guess. And then I'll cube root or raise it to the 1/3 exponent. And now we have a formula. As long as the x value is chosen between negative epsilon plus 1 to the 1/3 or epsilon plus 1 to the positive 1/3, we will be able to find an x value that gives closer than, epsilon to y. It's just the way the argument goes. And again, no matter what they say, if E is equal to 0.1 or 0.01 or 0.001, all right, they can come back and say, okay, I never think it gets closer than 0.0001. You could just say, okay, I'm going to put this into my formula, and immediately you have an X value, which is going to give a limit or a value of Y closer than 3. So we can refute no matter what number they come up with. we can say, oh, we can get closer than your value. So the argument is, okay, well, no matter what they tell us, we can get closer. That means we can get all the way as close to 3 as we ever need to be, and therefore we can get exactly to 3. So that's the way the argument goes. By the way, the author of your book, because they like the absolute value inequality thing, what they will do is they'll actually subtract 1 and they'll say x minus 1. And so they're basically subtracting 1 on both sides or all 3 sides. So let's say x minus 1 is less than epsilon plus 1 to the 1/3 minus 1. And over here you'd have negative epsilon plus 1 to the 1/3 minus 1, because they want the x minus 1 in here. X minus 1 is the difference between x and 1. Remember, 1 is our limit. So they're saying the difference is always smaller than this thing right here. If you're asked to put in one answer, which you are sometimes in WebAssign, you just have to put in the smaller answer. So numerically, we would look at these two values, right? And we would take the smaller one. So just always remember to take the smaller distance if they ask you to put in the one answer for the distance away from x that you need to be. All right, so that's the example where, we kind of saw it coming already. I wanted to show you the example with a number in it, an example with a letter in it, so you can see how that's done. I have one more example for us to do. This one's a little more complicated function, and you're not going to know a way to plug things in directly because you won't be able to get an answer. All right, so here's my second example. This function is going to be the, up here, the negative ln of x. There. And we're looking to see what happens when x approaches 0. And if it's not visible for you, I have 0 with a little plus sign, which means we're only choosing values that are to the right or greater than 0. So we're going to try to find out what happens to this function when x approaches 0 from the positive side. All right, so let me turn off this guy, and I will turn on my negative ln x graph. So let me do that. Recenter this thing. So that's the negative ln x graph. If you remember the ln x graph, it's kind of going like this. The negative does a vertical flip, so it flips over the x-axis, and therefore instead of going up, it's going down. All right, and we're looking to see what happens around 0, and you can kind of see it goes off the screen. If we try to put in 0 in for x, it'll say it's undefined. So we're trying to figure out what the answer is to this limit, and the table's not giving us the answer directly. Well, looking at this thing, it seems to just go up and up and up and up. So maybe we think the answer is infinity, right? Maybe it just goes up to infinity, and that's the answer for the limit. Just goes off the screen forever. So let me show you how to demonstrate that, to verify that. So again, we're going to validate a limit. So here we're validating the answer is infinity. On the previous problem, we validated the answer was 3. So now we're saying the answer is infinity, much more confusing on the face of it. And what we're going to do that is we're going to refute the claim. If it's not an infinity, it must have an upper limit. It never gets over, 1,000 or 10 or a million or whatever. You have to say some number. It never goes over. Otherwise, it can keep going forever, and that would go off to infinity. So if someone's going to say, no, I don't think the limit's infinity, then they must be thinking it stops somewhere, right? And no matter where they think it stops, we can say it goes higher than that. So that's the way we're going to be able to say that no matter where, we can go higher forever. So therefore, it will be infinity. So the argument is someone says, the y values never go above, for example, 10, which is a smaller number. So all we need to do is find an x value that gives a y value above 10. Okay. So we know right here that y, hold on 1 second. Okay, I'm back. Sorry about that. So we're trying to find where y can be greater than 10. Right? They're saying y could never be less than 10, so we're going to say, y is going to be bigger than 10. So I know what the y function is. It's negative ln x. And then I can solve for x here. So I can multiply both sides by -1. If you remember, when you multiply both sides by a negative, you reverse the inequality sign. And to undo a natural log, we just raise both sides to or we put the base e to both sides. And that will give us x is less than e to the -10. So as long as we have an x value that's less than e to the -10, we will guarantee that we'll have a y value bigger than 10. So here's our little graph here. And notice we can't put in 0. We can put a number close to 0, like 0.1, but that's not bigger than 10. 0.001, 001, there we go. And that's not bigger than 10. The one I just did was pretty close to 10. But, there's going to be a time in which we want to stop guessing. We want a way of doing this much easier than just guessing forever. And we just found it. We know that as long as we have an x number less than e to the -10, the y value will be bigger than the y value will be bigger than 10 when the x value is less than e to the -10. So let me compute e to the -10. And that's 0.00004. So let me do that. 0. Got to put it in my table, sorry. 0.00, there are 4 zeros. Okay. And you can see that when I get down to that level, I can even put the 5 in there, that it's still bigger than 10, right? That's the place I know as long as x is smaller than that value, the y value is bigger than 10. So that, again, is the way of saying, you don't think it gets above 10? I can get above 10. And if they say, well, what about 100 or what about 1,000 or a million? It doesn't really matter. We can do this exact calculation with a letter instead of a number. So, for example, suppose they say some maximum value m. M could be a million or whatever it is, right? We can do this exact same calculation, and we end up with a formula that allows us to say, okay, no matter what m you choose, whatever you think is the maximum value for this thing, we are going to say, okay, x just has to be smaller than e to the m. So if they say a million, we just do e to the -1,000,000, and that will be an x value, which gets closer and closer and closer, specifically closer than 1,000,000. All right, so there's a couple of examples of verifying limits. One where we try to verify a limit as x goes to 1, y went to 3. And the second one here, we verified when x went to 0 from the right-hand side, y got infinitely big. So these are the kinds of problems you'll see in 2.4. A little bit esoteric, but definitely mathematicians care about precision and knowing when they can definitively say something. So this is the idea about how we can definitively say a limit actually exists and is the number we think it is, as opposed to we think it is, we're guessing, we're intuiting. This is the way to reassure us or verify that that limit exists. All right, hopefully you found this video useful. And once again, if you have any questions, just reach out and I'll help you the best I can.